The approach we just used, starting with a line between 2 points on the curve and taking the limit as delta x approaches 0, is a process called differentiating from first principles. It's the underlying basis of differential calculus. But in practice, engineers rarely do this from scratch. We just saw from first principles delta, which we just dy over dt of x. Often quantity y. The dot notation is often used to represent derivatives. The approach we just used, starting with a line between 2 points on the curve and taking the limit as delta x approaches 0, is a process called differentiating from first principles. It's the underlying basis of differential calculus. But in practice, engineers rarely do this from scratch. We just saw that the derivative of x cubed is 3x squared. This pattern isn't unique to that one function. It works for any function of the form x to the power of n. The derivative is obtained by multiplying by the power and reducing that power by 1. Instead of deriving everything from scratch, engineers use tables of standard derivatives for the functions we see again and again, like sine, cosine, exponential functions, or square root functions. Let's look at a few examples. The derivative of a constant value is 0, because it has no slope. And a straight line has a constant slope, so its derivative is a constant value. Sine and cosine functions appear all the time in engineering, especially in systems that vary cyclically with time, like alternating current circuits. This graph shows sine of x. At the peaks, where the function reaches a maximum, the slope is 0. And where the curve crosses the horizontal axis, the slope is at its steepest, corresponding to either its minimum or maximum value. The derivative of sine of x is cosine of x. Similarly, the derivative of cosine of x is negative sine of x. The negative is needed for the slope to have the correct sign, positive where cosine is rising, and negative where it's falling. Another important function is the exponential function. What makes it remarkable is that at every point, the slope is exactly equal to the value of the function itself. The larger the value, the faster it grows. Exponential behavior shows up whenever the rate of change of a quantity depends on how much of that quantity already exists, like the charge building up in a capacitor, or radioactive decay, where more atoms means more decay events. In most engineering applications, we're not dealing with a single simple function, but a combination of more complicated functions. Fortunately, a few straightforward rules save us from having to differentiate from first principles every time. The first is the linearity rule. When two functions are added together, the derivative of the whole function is just the sum of the derivatives of the two individual functions. This doesn't work when the functions are multiplied together though, because when both functions are changing, their rates of change interact. In these cases, the product rule needs to be used. The derivative of the product of two functions u and v is the derivative of u multiplied by v, plus u multiplied by the derivative of v. Similarly, the quotient rule should be used when one function is divided by another. And finally, there's the chain rule. To find the derivative when one function is nested inside another, you differentiate the outer function as if the inner part were just a single variable, and multiply it by the derivative of the inner function. Here's an example where the inner function u is 3x, and the outer function v is sine of u. The derivative of this function is equal to the derivative of v with respect to u, which is cosine of u, multiplied by the derivative of u. Having 3x inside the sine term instead of just x means that as x increases, the input to the sine curve increases 3 times faster. This makes the slope of the curve 3 times steeper at every point, which is why you need to multiply by the derivative of u to get the correct slope. With these 4 simple rules and the table of derivatives for common functions, you can differentiate a huge range of complicated functions relatively easily.
The internet is the biggest wealth creation engine to ever exist. Sadly, only a relative few have been able to participate in it. At Replit, we believe that the next generation of software creators can come from anywhere in the world. And that starts with access.
The derivative gives us a really useful tool for exploring the behavior of a function. If we plot this function on a graph, for example, you'll notice that wherever the derivative is 0, the function is at a local minimum or maximum. This happens because the slope of the curve goes from being negative to being positive at a minimum, and from being positive to negative at a maximum. In both cases, the slope must pass through 0 at the turning point. This is a powerful application of calculus. If we want to find the maximum or minimum values of a function, we can just take its derivative and find where it's equal to 0. These points where the slope of a curve becomes flat are called stationary points. To figure out if a stationary point is a maximum or a minimum, all we need to do is look at how the slope itself changes around that point. And we can do that by taking the derivative of the derivative, which is called the second derivative. The second derivative tells us about the curvature of the function. If it's positive, the derivative has a positive slope, so the curve is bending upwards, which means we're at a local minimum. And if it's negative, the derivative has a negative slope, so the curve bends downwards and we're at a local maximum. There's a third type of stationary point called an inflection point, where the curve doesn't turn back on itself, but its curvature reverses. At a stationary inflection point, both the first and second derivatives are 0, and the second derivative changes sign to reflect the curvature reversal. Now let's see why this matters in the real world. Imagine a function that represents the temperature along a nuclear fuel rod. We want to model how this temperature distribution changes over time. This can be done using the heat equation. It tells us that the rate at which temperature changes over time depends on a material property called thermal diffusivity, and how temperature is distributed along the rod, represented by the second derivative of temperature with respect to the position x. The second derivative appears in the equation because heat will flow away from local hotspots, where the second derivative is negative, toward cooler regions where the second derivative is positive. It's the second derivative that determines the direction of heat flow. Away by the second derivative rate time. This can be done using the heat equation. It tells us that the rate at which temperature changes over time depends on a material property called thermal diffusivity, and how temperature is distributed along the rod, represented by the second derivative of temperature with respect to the position x. The second derivative appears in the equation because heat will flow away from local hotspots, where the second derivative is negative, toward cooler regions where the second derivative is positive. It's the second derivative that determines the direction of heat flow. Many physical processes follow similar laws, where quantities spread over time from regions of high to low concentration. Fick's second law of diffusion, for example, is used to model the movement of atoms in a solid, or the dispersion of contaminants in a liquid. In all such cases, calculus provides the framework for modeling how these quantities change over time. You might have noticed that these equations use a slightly different notation for the derivative. So far, we've only discussed derivatives of functions that depend on one variable, like time or position, but many real-world quantities depend on two variables or more. The curly d symbol tells us we're taking a partial derivative, which means we're looking at how temperature changes with respect to one variable while holding the other constant. The partial derivative of temperature with respect to time describes how the temperature at any fixed point on the rod changes with time. And the partial derivative with respect to position describes how temperature varies along the length of the rod at a single instant in time. Take a simple function that depends on variables x and t. To take the partial derivative with respect to x, we differentiate by considering t to be a constant. And to take the partial derivative with respect to t, we consider x to be a constant. Differentiation takes a function and gives you the rate of change as you move along it. In some cases, though, the rate of change is what we already know, and we want to figure out the function itself. Imagine a function that tells you how some quantity changes with time, a power consumption curve for an electric motor, for example. It shows higher power consumption during startup and lower consumption during steady operation. Power is the rate at which energy is consumed, measured in joules per second, so this curve effectively represents the derivative of the total energy consumption with respect to time. To figure out the total energy consumed over a set time period, we need to add up all of the small instantaneous changes. This process, accumulating all these infinitesimal changes to find the total quantity, is called integration. It's the reverse of differentiation.
Stop taking meeting notes and let ClickUp AI Note Taker do it for you. It allows you to focus on your meeting.
Graphically, integration corresponds to finding the area under a curve. To see why this is, imagine dividing the region under the curve into loads of thin vertical rectangles. Each rectangle has a width that corresponds to a small change in x, and a height equal to the value of the curve at that x. And so the rectangle approximates a tiny contribution to the total. 1,300 joules per second consumed over 0.1 seconds is 130 joules. To obtain the total accumulated quantity up to a certain point, you just add up all of the tiny contributions up to that point.